Now, why is this ride that we're representing by this model, why is that ride fun? Well, one answer is that the direction of your motion keeps changing, and it keeps changing at different rates. Another answer is simply that you have a variable acceleration, so you feel varying forces. It moves you around and speeds you up and slows you down in different directions, tries to throw you off one way, tries to throw you off the other. Under a controlled mechanical device, that can be really fun if you don't get motion sickness. Okay, so we want to get a handle on what's the acceleration. Well, the acceleration of this thing mathematically is just the second derivative of the r function. And we can easily take the second derivative. Now, I'm not going to write it down. It would be easy to take the derivative of this mess down here. That'd be a little bit long, but there's nothing in there but sines and cosines of pi over 3t and 2 pi over 3t. So the derivatives are not difficult. You're going to get, here you have 4 terms in the derivative. The second derivative will have 8 terms. That's not a bad derivative. This would be kind of a bad derivative because you have a square root of a fairly complicated function. You're going to have to use the chain rule a whole bunch of times. This one doesn't even involve the chain rule except at one step, the inner function of your sine or cosine function. So the acceleration, easy, but a little long. At any point, your direction with respect to, well, the direction of your motion and your speed are going to tend to change. And the rate at which your velocity changes, the velocity being the direction and magnitude of your motion, the direction and the speed of your motion, will typically have, the acceleration will typically have components which are parallel and perpendicular to your direction of motion. So if we represent a typical r vector at some time t, and a typical velocity vector. Velocity at any instant is going to be tangent to this curve, and maybe the velocity vector is in this direction. Now that's going to be the derivative function, the r prime function. And that's your velocity. And there's also an acceleration function, the direction in which you are being sped up or slowed down, and also the direction in which you're being moved toward or away from the center. So maybe our r prime function at this instant looks like, or our acceleration function, our r double prime, looks like this. This would be the acceleration. Now, as I just said, some of that acceleration is in the direction of your velocity, but some of it is perpendicular to the direction of your velocity. And the sensation of being sped up and the sensation of having your direction changed are really what makes this ride fun. Analyzing it mathematically might not be that much fun, but if we project this vector onto this vector, we get a vector projection here. And if we subtract this projection from the original vector, we get a vector perpendicular, which is also a projection in the perpendicular direction. So we have the component of the vector, the component of r double prime in the direction of r prime, that would be this vector, and the component of r double prime perpendicular to r prime. If we can calculate r double prime, and as I've said, it's not difficult to take a second derivative of this function, just a little messy, we can use the dot product to calculate the projection vector. And we can use the dot, and having obtained the projection vector, we can subtract it from the original vector to obtain the component perpendicular to our motion. So that using vector techniques that we learned previously in the course, we can gain a tremendous amount of information about this motion, which could be valuable in, for example, designing the apparatus. We don't want these accelerations to be too great, because the greater the acceleration, the greater the forces the various components are going to experience, and one of those components is, of course, the rider, whom you don't want to injure. And we also get an idea of how the acceleration changes with the velocity, which contributes to the sensation of the ride. Now, we're not going to analyze that for this function in great depth, but we see how the techniques that we've learned regarding the projections and magnitudes of vectors can be very useful in analyzing a complex motion.